All right, everybody, welcome. We're going to talk about optimization in this lesson. Okay, optimization is the maximizing or minimizing of quantities under given constraints or given conditions. Okay, and you'll see lots of examples in the lessons coming up. Typically when we do these problems, they're going to be a little bit wordy, okay? But we're going to be searching for really two equations that we're going to have to build based on what we're doing here. One is called the optimization equation. The other is the constraint equation. Let's go through these things. The optimization equation is an equation for what it is we want to maximize or minimize, okay? The constraint equation is an equation that represents the given conditions or given constants, okay? Both will have variables within these equations, but a big difference is with the optimization equation, we're going to have variables on both sides of the equation, and with the constraint equation, one side of the equation will be set equal to a given constant. Similarly to related rates problems, it's often going to be helpful to draw and label a diagram to help us get going, not always, but often. Unlike with related rates problems, we are not doing implicit differentiation here. We're going to be able to take derivatives with respect to whatever variable it is that's present in the problem, okay? So for example, like if I had area equals pi r squared and I was talking related rates, taking the derivative with respect to t is implicit differentiation. We get dA over dt equals 2 pi r times dr over dt. Well, here, if we have area equals pi r squared, and we're interested in finding a value of r that maximizes or minimizes the area, we're going to take the derivative with respect to r. So I could write this as dA over dr equals, and it would just be 2 pi r on the right, because we're taking the derivative with respect to r, okay? Or even more simply here, we could just write a prime equals 2 pi r. Okay, so you'll see that going on. There's not going to be this dt stuff, okay? Let's take a look, all right, to how this stuff works. In the first set of examples, we'll go through 4 examples. They're not too bad. And then in the second video, we'll go through some more complicated, complex examples, okay? But here we go. Two numbers have a sum of 10. What is the maximum possible product of the two numbers? Well, there's a lot of ways to add two numbers up to 10. 1 and 9, 2 and 8, 12 and negative 2, right? 20 and negative 10. There's an infinite number of ways to add any two numbers to the number 10, but there's only one largest possible product. Let's figure out what that is, okay? So look, the constraint equation, that's going to be equal to some number, in this case 10. We need to represent an equation that represents two numbers adding to 10. So we can pick whatever letters we want. I'm going to use x and y for our two numbers. So the constraint here is that x plus y, these two numbers, have to add up to 10. The optimization now is the thing I want to maximize or minimize. What is the maximum possible product of these two numbers? So I'm going to use p for product. And how do I find the product of two numbers? Well, we multiply. So using the letters x and y, the constraint is that they add to 10. That's the purple equation. We want to find the max product, p equals xy. And like I commented up here, notice we have variables on both sides of the equation for the optimization. I want to maximize that in terms of x and y. The constraint is set equal to a given constant, okay? Now, once you get this far in a problem, the rest of what we do is going to be very, very similar for all these problems. The hardest part is coming up with these first two equations. From here on out, what we do is very procedural. Ultimately, I want to find the max value of the product. So how do we find maxes and mins? We take derivatives, right? Issue is that right now this is in terms of two variables. Okay, excuse me, I didn't mean to erase that. This is in terms of two variables. Before we take the derivative, we want to get p product in terms of a single variable. So what you're typically going to find is that after we set up our equations, we're going to go back and we're going to solve the constraint for a single variable. All that means is we're going to choose one of the letters to get by itself in the constraint equation. Rule of thumb, usually choose the one that's easier to get by itself. Here, it doesn't much matter. I'm just going to get y by itself, and that would equal 10 minus x. So get the constraint equation solved for a single variable. Then we end up subbing that in to the optimization equation. So where, notice, y is equal to 10 minus x, I'm going to replace that letter y with 10 minus x here. And now we've got our optimization equation product in terms of a single variable x. That's what we want. Once you've done this, you can now actually take the derivative if you want. I'm not gonna, because I don't want to use the product rule. I'm gonna clean this up a little bit by distributing the x, right? And now I can very easily take the derivative. We wanted max product, so I can write this as dp over dx. I'm taking the derivative with respect to x here. You can also more simply just write p prime. That's up to you guys, okay? But taking the derivative with respect to x, we simply get 10 minus 2x back for our first derivative, okay? And so now, you know, think about what we're doing. We're trying to find a max min, so we took the derivative. We have to verify max min, so what should we do? We should set this equal to 0, solve for x, and do a little bit of verification to see if we got our max or our min. Solving for x, the derivative is 0 when x is 5. So I'll go ahead and do my first derivative test here. When x is 5, the first derivative is 0. And again, I'm just going to test numbers in my first derivative to see if they're positive or negative. If I plug a number less than 5 in for x, it looks like that's going to come back positive. So product is increasing. If I take a number bigger than 5 and plug it in for x, like 6, 10 minus 12 is negative. Product is decreasing. We indeed found a max at x equals 5. Okay, so we do need to show this work to verify that we have a max. And now let's think about what the question ultimately wants. It says, what is the maximum possible product of the two numbers? Okay, so we know we're going to get a max product when x is 5. Here is the equation for product right here. So if I want now, I can go back and get the y value. Where do we go to get that? Back to the constraint. Notice, if we know what x is, we can solve for y. Subbing in 5 for x, it looks like y is also going to be 5 here. And the max possible product is x times y, so max product 5 times 5 is 25. Take any two numbers that add to 10, the largest that they'll ever multiply to is 25 when both of those numbers are 5. Okay, and there's your first optimization question. Constraint, variable set equal to a constant. Optimization, the thing we want to max or minimize. Sub in, derive, go from there. Let's try the next one. Two positive numbers have a product of 24. Find the two numbers such that the first plus twice the second is a minimum. So again, we're looking for two numbers. I'm going to call them A and B here, okay? And what's the constraint? Two positive numbers have a product of 24. So this time we know what they multiply to. So the constraint, A times B is 24 here. Now, our optimization. Find two numbers such that the first plus twice the second is a minimum. I'm going to let A be the first. I'm going to let B be the second. A plus 2B. The first plus twice the second. We want that to be a minimum. We don't know what that equals. We got to call it whatever we want. I'm just going to use the letter V to represent some value. I used the letter P up here for product. Product was X times Y. Here we're timesing B by 2 and adding it. It's not so much a sum. It's not so much a product. I'm just using the letter V to represent the value of A plus 2B. Okay? So again, I've got the constraint equal to a constant. I've got the optimization with variables on both sides of the equation. Now we're going to choose a letter to get by itself. I guess I'll go ahead and solve for B here. B would be 24 over A. So I'm going to replace the letter B in the optimization equation with that. And we get volume equals A plus 48 over A, or 48 times A to the negative first, kind of anticipating that we're going to take the derivative, okay? But again, now we've got our optimization in terms of a single variable A. Taking the derivative. I'll call it v prime. You can call it dv over dA if you want. We're taking the derivative with respect to a. So I'm going to get 1 minus 48a to the negative second, or 1 minus 48 over a squared. There's the derivative of the value we're looking for. Okay, so what are we going to do? We're going to set that equal to 0 to find the critical point. I'll add the fraction. I'll multiply by a squared. And taking the square root, a is going to be the square root of 48. Notice we're dealing with two positive numbers, so I'm not going to worry about the plus or minus. And that's 16 times 3, so that's 4 radical 3 if I simplify. Okay? Now to test for max min, my number line, I'm going to cut off at 0 because, again, two positive numbers, so I'm on the open interval 0, infinity. When a is 4 radical 3, the derivative was 0. If I take a number less than 4 radical 3, like 1's an easy number, and I plug it in to v prime. Let's see, if I plug 1 in for a, I get 1 minus 48 over 1 minus 48, that's negative. So it looks like value is decreasing. If I take a number bigger than 4 radical 3, let's see, a squared is 48. So I could use 7, right? 49 is bigger than 48, so 7 is going to be bigger than 4 radical 3. And again, use a calculator to make sure you're using numbers bigger and smaller than the critical point. But if I plug, let's see, like 7 into this for a, we get 1 minus 48 over 49, which is going to be, let's see, some positive value. It's not going to be too big, but it will be positive. And so we're increasing. Okay, and again, just take your time checking your signs and all that good stuff, okay? But it looks like we indeed have a min when a equals 4 radical 3. Okay? And what are we looking for? Find the two numbers such that the first plus twice the second is a min. So we've got the a value. We still need to get the b value. Again, once you got one value and you need the other, go back to your constraint. That's going to allow you to solve for the other. So look, if I know that a is 4 radical 3, then b is going to be 24 divided by that. 24 over 4 is 6. And if I clean this up just a little bit, looks like b is going to be 2 radical 3. Okay, so those are the smallest two positive numbers whose product is 24, and the smallest possible sum where twice 1 plus the second is a min. Okay, that's the idea here. All right, moving on. What is the minimum amount of fencing required to enclose a rectangular field of 100 square meters? Here's one where I'll draw a diagram. So we're enclosing this rectangular field. Before we can really come up with constraint equations or any equations, we need some variables here, okay? It's a rectangle. You can call it whatever you want, but I'm going to call this x. I'm going to call that y, okay? And what do we know? The opposite sides should be congruent here. We also know that we want this to have an area of 100 square meters. Now that I have some variables here, I can build that equation for the constraint. How do we find area? We multiply the dimensions. So here, x times y needs to equal 100 square meters. There's our constraint, set equal to a constant. Now the optimization, what are we looking to minimize? Here we want the minimum amount of fencing required to enclose this rectangle. Well, if you think about it, the amount of fencing is given by, more or less, the perimeter of this thing. To get the total amount of fencing, we've got to add up the 4 sides. Well, it looks like we're going to have 2 sides of length x and 2 sides of length y. And again, we need to set this equal to some variable. You can call it p for perimeter if you want. I'm going to use the letter f representing the amount of fencing. Again, it's up to us to set these equations up using whatever letters we choose. Okay, so I did f for fencing equals 2x plus 2y under the given constraint that x times y is 100. Okay, but again, constraint equal to some number, optimization variables on both sides. Now, again, let's choose a letter to get by itself. I'll just go with y here. Y is 100 over x, and that's what I'm going to sub in to my optimization. And cleaning this up a little bit, that's 200 over x, or 200 times x to the negative first. Okay, so I'm going to take the derivative with respect to x here. I'll call this f prime, and we get 2 minus 200 over x squared. Okay. And now again, we'll set this equal to 0. Notice this is undefined at 0 in the denominator there, but we're not going to have a length of a side of 0, so we can ignore that critical point. Let's see, adding the fraction over. So 2x squared is 200, so x squared is 100, and x is plus or minus 10, but we can reject the 10 again because we're dealing with lengths of sides, okay? So we're getting the x value of 10. So again, I can set up my number line to do the test here. What I'm actually going to do, though, is I'm going to, just to remind you, we can also use the second derivative test for max min. So look, if I take the second derivative here, f double prime is going to be, it looks like negative 400 x to the negative third, or negative 400 over x cubed, okay? So remember, to look at the second derivative test for max min, we look at the sign of the second derivative at our critical point. The critical point's at 10. I want to know, what is f double prime of 10? Let's see. Well, the numerator's negative, the bottom is positive, so this is going to be less than 0. Okay, f double prime of 10 is less than 0. What does that mean? It means the function's going to be concave. Let's see, it should be concave down. Okay. Let me double check here. I should be getting a min, so I'm thinking the second derivative should be positive. Did I make a mistake? Let's see. Negative 400x to the negative third looks good, right? Well, boy. Bear with me just for a second here, folks. For some reason, I'm having a brain fart. I know the x value's good. It should be coming back a min, though. Let me test with my first derivative test here. So let me keep this and do a number line here. Critical point was at 10. And if I take a number less than 10, like 1, I'm going to get 2 minus 200 over 1. That's negative, so we're indeed decreasing. So it's looking like a min. If I plug a number bigger than 10 in there, I'm going to get 2 minus, if I plug like 12 in, let's see, 200 over 144. That's a fraction less than 2. 2 minus that will be positive. Okay, so we definitely have our min at x equals 10. Okay? Not sure why the second derivative test is not coming back that way. I'm getting negative. That would be concave. That should be concave down. Well, look, forget this for the time being. I'll come back to this in a moment. I don't want to make things bad. Okay, this is coming out perfect right over here doing this test. Okay, we do get a min when x is 10. And again, what are we trying to do here? What is the minimum amount of fencing required? So the fencing is given by 2x plus 2y. I can come back here and solve for y now that I know x. X was 10, y is also 10. So the minimum amount of fencing, if I sub 10 in for both x and y, it looks like we're going with 40 meters of fencing. In fact, if x and y are both 10, it looks like the largest possible rectangle is actually what? A square, okay, of side length 10. Okay. And that is absolutely the correct answer, okay? 40 meters to enclose 100 square meters. Oh, I see. I made a careless mistake up here. That's why it didn't work. That should be a negative 2, which I erased. Now, real quick to go through the second derivative test correctly. My bad, folks. Taking the second derivative, we actually get positive 400x to the negative third. Okay, so again, if I evaluate this at the critical point, if I plug 10 in for x, that's going to be positive function is concave down with a slope of 0, it must be a max then. Okay, oh geez, I am really killing this, aren't I? If it's positive, it's not concave down, it's concave up with a slope of 0, relative min. Finally, everything comes together. Sorry about that. Okay, hopefully it wasn't too painful to sit through that botched second derivative test. But again, the point is these things should come out the same. By doing it twice, I realized I made a mistake over here, and then was able to correct it, okay? But again, you know, I'm not too picky about the way you go and verify your max mins. Really what I'm trying to show you, you can do first derivative test, you can do second derivative test. There's really different ways that you can go about this, okay? Point is to try and be careful, and you know, if you make mistakes, it happens. Obviously, it happens to me, but we fix them. Okay, one more example here for this video. We have 1,000 feet of fencing material to enclose a rectangular play area. A building is on one side of the play area, and so will not need fencing there. What is the largest area we can enclose? So here we know we have 1,000 feet of material to work with. What's the largest play area we can enclose? So here I'm going to draw this kind of like a bird's eye view. So we're looking down on this rectangular play area. Now here is the building, and so we don't have any fencing material there, okay? I do need variables. I'm going to go this X, and I'm going to call this Y. So if you think about it, the total fencing material is these three sides. Side of length Y plus a side of length X plus another side of length Y. Okay? So there's our constraint. Okay, think about what the constraint's going to look like. 1,000 feet of fencing material. If I add those three sides together, it's got to add up to 1,000. So 1x plus 2 lengths of side y adds up to 1,000. Now, what are we looking to do here? We are looking to find the largest possible area. We want to maximize the area. I'm going to call it A for area equals, well, it's a rectangle, so it's going to be x times y here. Okay, and there's our optimization and constraint. And now going through the process, let's solve the constraint for a single variable. I think x is a little easier to get alone because we won't have to divide by 2. So x is 1,000 minus 2y, and I'll replace x in my optimization equation with that. Again, if I want to take the derivative using the product rule, I can do that, but I'm more simply going to distribute the y. Oops. And now I'll take the derivative of this with respect to y. A prime is what I'll write, but if you want to write dA over dy, you may do so. But there's what the derivative looks like, 1,000 minus 4y. So again, we can do a number line test, we can do a second derivative test, and yet even a third way to test for max min would actually be to look at the graph of A prime. If you think about it, A prime, that's just a linear equation. It's got an intercept up at 1,000 and a slope of -4, so it just looks like this. This is the graph of A prime. And what did we learn recently? We get a max or min based on the way the derivative changes signs. Well, think about it. A prime equals 0 right here. We can set that equal to 0 and solve easily. That ends up just being 250 for y. Okay, which is what we're calling this value. Okay. This is the graph of basically y versus A prime. Call this the y-axis. This is A prime. Okay. But look, think about what's going on. A prime is positive to the left and negative to the right. Guess we have a max. Okay, so again, we really have 3 ways of testing for max min. Your typical first derivative test with the number line, your second derivative test by looking at the sign of the second derivative to determine concavity and whether we're at the top or bottom, as well as what we more recently went through looking at the graph of the first derivative and sign changes to determine, okay? So again, ultimately, you want to know all these different ways to test for max min. Okay, and there you go. In any given problem, if I don't specify which way to test, it's up to you to test any way you best see fit, okay? But again, lots of ways, and the important thing is that you're finding a way to back your work up. Yes, this is a max. Yes, this is a min, okay? Whatever. In this case, we have a max. Derivative changed from positive to negative. And so again, the question is, what is the largest possible area we can enclose? So again, I can come back up here. Now that I know what y is, I can solve for x. I can plug them in here, and I can get that max area. But we don't actually need to get x to get the max area. If you think about it, we've got an area equation just in terms of y. So if you realize that, you can actually save yourself a second or two of work. You don't even have to get the x value. We're going to get the max area when y is 250, so we could actually plug that right into this. Okay, I'm just using that with the y value. Whether you went back and solved for x, or you're just doing it this way, your max possible area should be, and I'm just punching it in, so bear with me, 125,000 square feet. Okay, folks. So again, the moral is careful reading through these. If you need a diagram and you need some variables so you can notate stuff, put it on there. We're taking the derivative with respect to whatever variable we choose. We typically are going to have two equations to start. The constraint, which is equal to a constant. The optimization, which has variables on both sides. And after we sub into the optimization, we take the derivative to maximize or minimize it. Okay, so a lot going on. Try to get this down, and then in the next lesson, we'll look at some more advanced examples. Reach out if you need help. Have a great day. Thanks.